Colligative properties, definition, principles, mathematical treatment, and applications. The physical properties of matter are generally classified into extensive and intensive properties. Extensive properties, such as mass and volume, depend on the quantity of material present, whereas intensive properties, including density, refractive index, and concentration, are independent of sample size. Within the category of intensive properties exists a specialized subgroup known as colligative properties. These properties are unique to solutions and depend exclusively on the number of dissolved solute particles relative to the amount of solvent, rather than on the chemical identity of the solute itself. The term colligative originates from the Latin word colligatus, meaning bound together, reflecting the collective influence of dissolved particles on solution behavior. The scientific understanding of colligative properties was established during the 19th century through the pioneering work of François-Marie Raoult and Jacobus Henricus van 't Hoff. Their studies provided the theoretical and mathematical basis for explaining how dissolved substances alter the thermodynamic properties of solvents. Colligative properties are among the most important concepts in physical chemistry because they explain the behavior of solutions in chemical, biological, environmental, and industrial systems. They are fundamental to antifreeze formulations, food preservation, pharmaceutical preparation, desalination technologies, cryopreservation, and molecular weight determination. Fundamental concept of colligative properties. When a solute dissolves in a solvent, the solute particles interfere with the physical processes occurring at the solvent surface and within the liquid phase. As a result, the thermodynamic properties of the solvent are altered. These changes arise because the addition of a solute reduces the chemical potential of the solvent and increases the system's entropy. Importantly, the magnitude of these effects depends on the concentration of dissolved particles rather than their chemical nature. For dilute ideal solutions, four major phenomena are recognized as colligative properties: vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Each property originates from the same thermodynamic principle: the reduction of the solvent's tendency to escape due to the presence of solute particles. In electrolyte solutions, the number of dissolved particles increases because ionic compounds dissociate into ions. This behavior is described by the van 't Hoff factor I, which accounts for the effective number of particles present in solution. For example, glucose remains molecular in water and has I approximately equals 1, whereas sodium chloride dissociates into sodium and chloride ions, and therefore exhibits I approximately equals 2. Vapor pressure lowering. Vapor pressure lowering is the decrease in the vapor pressure of a solvent after dissolution of a non-volatile solute. In a pure liquid, solvent molecules at the surface continuously escape into the vapor phase until equilibrium is established between evaporation and condensation. When a solute is introduced, some surface sites become occupied by solute particles, reducing the number of solvent molecules capable of escaping into the vapor phase. Consequently, the vapor pressure of the solution becomes lower than that of the pure solvent. This phenomenon was quantitatively described by Raoult in 1887 through Raoult's law: P equals X solvent times P0, where P is the vapor pressure of the solvent in solution, P0 is the vapor pressure of the pure solvent, and X solvent is the mole fraction of the solvent. The reduction in vapor pressure is expressed as delta P equals P0 minus P equals X solute P0. This equation demonstrates that the vapor pressure lowering depends directly on the concentration of solute particles. Experimentally, vapor pressure lowering can be measured using methods such as static manometry, differential vapor pressure analysis, and vapor pressure osmometry. These techniques compare the vapor pressure of a solution with that of the pure solvent under controlled conditions. The significance of vapor pressure lowering extends across numerous fields. In environmental systems, seawater evaporates more slowly than pure water because dissolved salts reduce its vapor pressure. In food preservation, concentrated sugar and salt solutions inhibit microbial growth partly by decreasing water activity. Pharmaceutical formulations also rely on controlled vapor pressure behavior to improve stability and shelf life. Boiling point elevation. Boiling point elevation refers to the increase in the boiling temperature of a solvent upon the addition of a non-volatile solute. A liquid boils when its vapor pressure becomes equal to the surrounding atmospheric pressure. Because dissolved solutes lower the vapor pressure of the solvent, additional thermal energy is required for the solution to reach the boiling point. The quantitative relationship for boiling point elevation is given by delta Tb equals IKBm, where delta Tb is the increase in boiling point, I is the Van Hoff factor, Kb is the molal boiling point elevation constant, and m is the molality of the solution. Boiling point elevation is experimentally determined using an instrument known as an ebullirometer, which measures the difference between the boiling points of a pure solvent and its solution. Historically, ebullioscopy became an important analytical technique for determining the molecular masses of dissolved substances. The practical importance of boiling point elevation is considerable. Automotive cooling systems employ ethylene glycol water mixtures that exhibit elevated boiling points, preventing overheating under high-temperature conditions. Industrial heat transfer systems similarly exploit this phenomenon to improve operational efficiency. In food processing, concentrated syrups possess higher boiling temperatures, affecting cooking and preservation processes. Freezing point depression. Freezing point depression is the lowering of the freezing temperature of a solvent when a solute is dissolved in it. During freezing, solvent molecules arrange themselves into an ordered crystalline structure. Dissolved solute particles disrupt this ordering process, requiring lower temperatures before crystallization can occur. The relationship governing freezing point depression is expressed as delta Tf equals IKFm, where delta Tf is the decrease in freezing point, I is the Van Hoff factor, Kf is the freezing point depression constant, and m is the molality of the solution. The freezing temperature of the solution is therefore Tf, solution, equals Tf, pure solvent, minus delta Tf. This property is commonly measured by cryoscopy, in which the freezing temperatures of the pure solvent and solution are carefully compared. Cryoscopic measurements historically provided an important method for determining the molecular masses of polymers and biological macromolecules. Freezing point depression has extensive practical applications. Sodium chloride and calcium chloride are routinely spread on icy roads because they lower the freezing point of water, causing ice to melt below 0 degrees Celsius. Antifreeze solutions in automobiles utilize ethylene glycol to prevent engine cooling fluids from freezing under winter conditions. In biology and medicine, cryoprotective agents such as glycerol and dimethyl sulfoxide are used to preserve cells, tissues, and vaccines by inhibiting ice crystal formation. Osmotic pressure. Osmotic pressure is another important colligative property associated with the movement of solvent molecules through a semi-permeable membrane. The phenomenon of osmosis was first observed in the 18th century by Jean-Antoine Nollet, who demonstrated that solvent molecules could migrate across animal membranes into concentrated solutions. Osmosis occurs when a semi-permeable membrane separates a pure solvent from a solution, or separates two solutions of different concentrations. The membrane permits the passage of solvent molecules but restricts solute movement. Solvent naturally flows toward the region of higher solute concentration until equilibrium is achieved. The pressure required to stop this solvent flow is termed osmotic pressure. Van 't Hoff demonstrated that osmotic pressure obeys an equation analogous to the ideal gas law, pi equals IMR T, where pi is the osmotic pressure, I is the Van 't Hoff factor, M is the molar concentration of the solute, R is the universal gas constant, and T is the absolute temperature. Alternatively, osmotic pressure may be expressed as pi equals I nRT divided by V. Experimental determination of osmotic pressure is carried out using membrane osmometers and vapor pressure osmometers. These methods are particularly valuable for determining the molecular masses of proteins, polymers, and biological macromolecules that cannot easily be analyzed using vaporization techniques. The significance of osmotic pressure is especially prominent in biological systems. Cell membranes behave as semi-permeable barriers, and osmotic balance regulates cell volume and physiological stability. Cells placed in hypertonic solutions lose water and shrink, whereas cells in hypotonic environments absorb water and may rupture. Osmotic principles are also central to kidney function, nutrient transport, and intravenous saline preparation. In industrial applications, reverse osmosis technology has become one of the most important methods for seawater desalination and water purification. Modern desalination plants employ high pressure to overcome osmotic pressure and force water through specialized membranes, producing potable water from saline sources. Thermodynamic basis of colligative properties. The thermodynamic origin of colligative properties lies in the reduction of solvent chemical potential upon mixing. Dissolution increases the entropy of the system because the solute and solvent molecules become more randomly distributed. This increase in disorder lowers the escaping tendency of solvent molecules and alters equilibrium conditions between liquid, vapor, and solid phases. As a consequence, the solvent exhibits lower vapor pressure, higher boiling temperature, lower freezing temperature, and measurable osmotic pressure. Modern statistical thermodynamics interprets these effects in terms of molecular probability distributions and intermolecular interactions. Determination of molecular mass. Historically, colligative properties became essential tools for determining molecular masses of dissolved compounds. Measurements of vapor pressure, lowering, boiling point elevation, freezing point depression, and osmotic pressure enable calculation of the number of dissolved particles present in solution. Because these properties depend only on particle concentration, accurate experimental measurements can provide molecular weight information for unknown compounds. Cryoscopy and ebullioscopy were extensively used in classical physical chemistry for organic molecules, whereas osmotic pressure measurements became particularly important for proteins and polymers with very high molecular masses. Limitations of colligative property laws. The classical equations describing colligative properties apply most accurately to dilute ideal solutions. Real systems often exhibit deviations due to intermolecular interactions, ion pairing, hydrogen bonding, or solute association and dissociation. Highly concentrated electrolyte solutions frequently require corrections involving activity coefficients and advanced thermodynamic models such as Debye-Huckel theory. Despite these limitations, colligative property relationships remain highly reliable for dilute solutions and continue to serve as foundational principles in physical chemistry and solution thermodynamics. In conclusion, Colligative properties constitute a fundamental group of solution properties that depend solely on the number of dissolved particles present in a solvent. The four principal colligative properties, vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure, arise from changes in solvent chemical potential and phase equilibrium caused by solute addition. The pioneering contributions of Raoul and Van 't Hoff established the mathematical and thermodynamic foundations of solution chemistry and transformed the understanding of molecular interactions in liquids. Today, colligative properties remain indispensable in chemistry, biology, medicine, materials science, environmental engineering, and industrial process design. Their applications range from antifreeze systems and food preservation to pharmaceutical formulations, desalination technologies, and molecular weight determination.